I will give a talk about the introduction to cosmology now. So I am Seishi in the research fellow in the School of Physics. At first, I will introduce you about expanding universe of the formulation. The current observational fact in the universe like that. So at first, our universe is homogeneous and isotropic. And also, our observation shows universe is expanding now. So this fact shows that the metric is given by homogeneous and isotropic metric. And also, of course, this metric is depend on the time and radius, but it doesn't depend on the angles. So this homogeneous and isotropic space is not for flat space, but also curved space also possible. For example, if you consider a spherical surface, for example, the surface on the Earth. So that means very saying roughly, the object of the curved two-dimensional object is embedded on the flat 3D space. So that means, at first we consider the flat 3-dimensional space, like this, with a constraint with radius a. This is a constant, and so if you use this constraint, then you can get the some constraint on the z. The z is given by this form, and this z is given by this one. So you can get this relation between the z and the x and y like this. So using this relation to here, then finally you can get this type of line element. So now this metric is not dependent on the direction of z. So this situation is this situation is like that. So on the two-dimensional surface, if you see from this point or this point, then the side thing looks like single. So that means the homogeneous and isotropic in anywhere. And in this page, I consider with the polar coordinates, then you can get just a moment. So previously I showed just the Descartes coordinate, and if you consider the polar coordinate, the polar coordinate on this two-dimensional. So x is the r tilde cosine of phi, and y is the r tilde sine phi. So you input here, then input to here, then you can get this form, and this form. So after this form, then if you take the r tilde is ra, define the scale of the radius by a, then finally you can get this form. So you can get the metric for the two-dimensional case is like, so the component of the GRR is given by here, and also the angle part, the d phi is given by this one and this one, like this. So now, so this case is like the curved 2D case. So, but the next we consider that. So what if we consider the 4-dimensional case? I mean the 1-dimensional time and 3-dimensional space with the curved space. Then the discussion is almost similar. So previously I showed the curved 2D case is like given by like this form. So if we consider on the 3-dimensional space, then just you change this part. The radius part is almost same, but I added this parameter k. So this case shows previous case shows just the spherical curvature, but it is also possible for the parabolic, let's say the hyperbolic surface is also possible for the constant curvature. I mean, if you take this k is a +1, I mean, this k equal +1 means the spherical surface. So the shape is like the closed universe like this. But if you take the k is minus, then it shows the hyperbolic space. So very similarly, this kind of a shape. The difference of this figure is like if you observe if you measure the radius from the top to this circle, then the 2 pi r, so circulate length, is smaller than just the 2 pi. But also, if you measure this radius on this circle, then the circular length is bigger than this flat space. And also, if you take the k equals 0, that just shows the flat space like this. And also the angular part is three-dimensional case. And so as I said, in the 2D case has some radius of the circular radius. Then we also put here, but time-dependent parameter here. This A is called as the scale factor. And so I wrote the three-dimensional constant curvature case like this. But if you want to consider just a Descartes coordinate, then you can relate this form to this part. But anyway, the important parameter is this k and a for the constant curvature flat spacetime. And so the physical meaning of this A, physical scale of this A is like, so if you consider some a coordinate like this, then the next time this coordinate is expanded, but this original x and y is not changed the scale, but of course the scale is not changed, but the physical scale is changing like this. So you can imagine that some balloon, if you write some coordinate on the balloon, then balloon is expanding, then the scale is changed, but the unit of the scale, it doesn't change. So this coordinate is called as the comoving coordinate. And so I wrote the curvature parameter here, but I explained before, so I skip here. And using the previous, using this form, then we can get a metric like this. So the component of the 0, 0 is just 1, and the off-diagonal part is 0, but this Gij for Descartes coordinate is given by like this. So using this metric, then you can calculate the connection defined by this one. Then non-zero term is just a three kind of the terms. One is this one is given by like this, and also the 0ij, this type of the connection give this path. And also everything is written by the space component. Then also it gives the this part. So if you consider the flat space, I mean the k equals 0, then this part becomes 0. So if the k is 0, then this part, only this part remains. Now I write this h is defined by the a dot a. It is called as a Hubble parameter. And the current observation shows the expansion rate is so h is just a parameter of this one. So we're saying roughly the h0, current h0 says the 67 kilometer per second and per megaparsec. And if you take the inverse of this, then it gives a scale of the age of a universe. So it gives the 14 billion years. By the way, so we can also calculate the connection from this result. Then curvature, Riemann tensor and Riemann curvature is the result is given by like this. So these are the Riemann Rich tensor is given like this, and also you can calculate the Rich scalar with this. Then finally you can get this form. So using the previous result, so we can derive the equation of motion for the universe from the Einstein equation. So, and I didn't explain I explained before about the space-time component, but also we have to mention about the matter side. So this is given by the energy momentum tensor. Now, we assume this energy momentum tensor is given by perfect fluid. So perfect fluid gives this energy momentum tensor by energy density and the pressure with this form. So using this energy momentum tensor, then this Einstein equation of the 0, component gives this type, this form, and the spatial component gives this form. So these two equations are called as the Friedmann equation. So if we combine these two equations, so at first you take the time derivative of this equation 1, and also using the Hubble dot form of the Hubble dot to the derivative of this, then finally you can get this form of equations. Actually, this equation is equivalent to the covariant derivative of the perfect fluids energy momentum tensor. So this equation says the kind of energy conservation. So normally, the case we follow the dynamics of the expanding universe. Normally, we use this equation with this equation, not to use this point, this equation. So I write the previous result here. And next, I show a solution of these equations. It is convenient to use this notation. So I write this this part becomes to this Rothschild. Then Rothschild is given by like this. And also, if you define the energy momentum tensor to this equation, then if you take define the pressure like this, then the form looks like the almost same equation like this. Now we consider the very special case, constant equation of state parameter W. W is defined by the ratio of the pressure and the energy density. So if we use this equation of the state, then this 3 prime given by like this. So if we solve this equation with constant W, then finally you can get the solution is like this form. So very saying roughly the Rothschild is proportional to the scale factor of power of -3, 1 plus W, like this. And also, we substitute this result to 3 prime. I'm sorry, this equation to substitute to here. Then you can get these equations, and so you can solve this equation as A equal this type or this form of the equation. So very saying roughly, if you take the H0t becomes very big, then the time dependence of the scale factor is given by like this. So the previous page I discussed with the general parameter of W, but now we consider the special value of W here. So if you consider the matter dominant case, that means the R tilde is only given by matter like energy density. So in this case, the pressure is very small comparing to the energy density, and also other component also are small. So in this case, this the energy conservation law like equation gives this equation. So in this case, the W is almost 0. Then the solution of this equation is given by form of this one. So the importance of the scale factor power of -3 is like just this energy density is diluted by the spatial expansion of the degrees of freedom is just a 3-dimensional. So like this. And also, if we use the W equals 0 to previous result, then you can get the scale factor is dependence of the time dependence of the scale factor is given by this form. And next, we consider a radiation dominant case. So in this case, the energy density and the pressure have this relation, and other component is negligible. So this case is relating to the W is 1/3. So using this result, then this result is given by like this. So the radiation energy density is given by proportional to the power of -4. So that physical meaning is like that. So the energy is diluted by spatial expansion, but also the radiation has the radiation is the wave. So the wavelength is also expanded. So that means the diluted factor is added from this spatial expansion with wavelength extension. Then totally it gives the -4. Also the Hubble, the radiation case, then the scale factor is depend on the this shape. And finally, we consider the vacuum energy dominant. In this case, the energy density tilde is almost given by the this is the cosmological constant. Then this W is almost given by -1. Then finally, you can get the dependence. If you take the W is -1, then this time dependence looks like power of 0. But if you take care in this calculation, then finally you can show this scale factor is proportional to the exponential like this. So physical meaning is like that. The energy within this commoving volume, the energy is given by this. And once it expands to this region, but the each energy density is constant. So if the volume is expanded, then the inside of the energy is increasing. So next time the expansion is more faster expanding. That is the reason of the exponential expansion. So previously, I write the Friedman equation with this. So normally we use the density parameter defined by here. So original equation is given by like this, and you divide by the 1/8 Hubble square. Then form is just given by 1 is these parameters. So we take this part is omega m, and this part is omega radiation part, and this part is the curvature and curvature omega, and this part is lambda, like omega lambda here. So total component, all the component is just a ratio is a 1. So this omega shows just a ratio, component ratio of the universe. So how many the matter or the radiation or curvature or dark energy is included. So the one of the observation of the CMB by the Planck satellite. So it observed the microwave, cosmic microwave background. So it says as the CMB. then the current observation shows the component ratio of the universe is given by like this. So we separate this matter is this omega B and omega C. This is called as the barium component and called the matter component. And here the barium means the proton and neutron. So it is well-known matters. And also this omega C called dark matter means the unknown neutral particle. So this doesn't include the neutron, but we don't know this called dark matter components, but just we write the omega C here. But it has a ratio 27% of the cold dark matter exists. And also, radiation is very negligible component, and also the curvature is almost zero. But the dark energy includes around the 69% component here. So currently we didn't include this component, but the almost component is explained by cold dark matter and dark energy. So this the fitting of this our universe component is explained by the matter and the dark energy. Then this model is called as the lambda CDM dark matter, lambda CDM model. So lambda means the dark energy part, and CDM is just a cold dark matter. So the universe is almost explained by this component. So as I said, so we don't know the 26 and 69 component is unknown. So why they are unknown component? I have to explain that like this. And actually, so this is the standard model table. So now we just consider the current observation. So that means we are observing the very low energy limit. So component of the high mass particle can be excluded from this component. Also, this radiation part is almost zero. So radiation component is explained by the photon and the neutrino. And this is also not main component of dark matter and dark energy. So the remaining is just the up quark and down quark and electron. But of course, the up quark and down quark form the barium. So barium means the proton and neutron. And also this electron is absorbed by this proton and neutron, including this barium component. So all the component of the table is excluded for the other components. I mean, dark matter or the dark energy. So this is the reason why these 90%, 95% is called as the unknown parameter. So this is not clear. Okay. So next, in this page, I calculate the age of the universe with previous density parameter. So as I said, the component of the universe is almost given by the matter component and the vacuum energy. Then we can eliminate this term because this part is very small. And so if you multiply the, so 1/8, 0 means the current, so the present value of the universe. Then, so this part becomes like this. And also, actually, this equation can be solved. Finally, you can get the this part, and you can perform the integration of this. Then finally, you can get the age of the universe is almost given by like this. So I am using the current parameters to here with the matter component is around 30%, and vacuum energy value is given by the 69% here. Then finally, you can get the age of universe is given by around the 14 giga year. And also, so we can define the particle horizon. This is very saying roughly. So the physical meaning is like that. So if we consider a point, then after the time of t, then the how radius of the this shape is interacted. So, for example, if we consider the massless particle, then so using a line element. Sorry, I use the k equals 0 here for simplicity, and also we set just the we just use the radius change, but don't use this angle change. Then this relation gives the relation between the dr and dt like this. The definition of the particle horizon is just to integrate over this line element. Then, so you can get the line element times scale factor, because this R do not have the physical meaning, but if we want to get the physical length, then this comoving length with the scale factor gives the physical length. So we have to define the particle horizon is given by like this. Then this R is just an integration of the line element, radius element. Then using this relation, and then the formula is given by like this. And so calculating with some blah blah blah, then finally you can get this result. So W is the constant parameter. So we're saying roughly the so if you take the W is radiation, so W is 1/3, then it gives the how it becomes and 2 2 and the 4, and so this factor, if the W equals 1/3, then this gives the 2 factor over 2. So that means the particle horizon is more broader than the normal CT, just twice as different. And finally, so in the end of this section, I give a rough sketch of the history of the universe. So actually, the current knowledge about the history of the universe is given by like this. So at first, we start from the inflation. In this age, the space is expanding with exponentially expand. And after the inflation, this scale is given by the Planck time scale. And after that, the universe is reheating. The name is reheating, but this is not second heating, but just a first heating, but we call it reheating here. Oops. So, and the heating happens, maybe some baryogenesis or dark matter lyric abundance happens around this time region, but I don't explain over here. And after that, in this time, so 10 to minus 10 seconds, then the electroweak phase transition is taking place. So in this event, so before this transition, almost particles are massive, and it is considered as the almost particles behave as the massless particle. But after the phase transition, then it is called as the Higgs background fields condensate. Then all the particles feel the force from this Higgs background. Then all the particles feel some friction from the Higgs. Then it looks like the particle achieved some mass, their mass. So this is the origin of the why all the particle has the mass. And after that, so around the time of the 10 to minus 4 second, then it is called as the QCD phase transition happens in this time. So in this time, before this QCD phase transition, then almost particle, I mean the almost quarks, the up and down, and the corresponding the gluon, this is the gauge field, is freely has some massless, almost massless motion, but after the QCD phase transition, then this up and down and the gluon combine together, then it forms the proton and neutron. So all the up and down and the gluon cannot seen after this time region, but it changed to proton and neutron. And next event happens on the edge of the universe is 1 second. And this time region, in this time region, the Big Bang nucleosynthesis happens. So in this time, in this era, so I said the proton and neutron are moving freely like this, but after the 1 second, so this is corresponding to the 1 MeV time, 1 MeV energy scale of the temperature. Then the binding, so the binding energy of the neutron and the proton is given by almost the order of the 1 MeV. So the temperature becomes below the 1 MeV. Then all these nucleons combine together. Then it forms the nucleons, nucleus, without I mean the atom, but without the electrons. So this is called as the big nucleosynthesis. And so actually this time region is given by almost a radiation dominant universe. But if the time takes on the 30,000 years, then the universe energy density of the universe shift from radiation dominant to matter dominant universe. So this is the time scale is given by like this. And much later than this era, so around the 380 100,000 years, then in this case, this time region is corresponding to the electron volt energy scale. Then, so next, what happened is like that. So proton bind the electrons, and that form the hydrogen or the other atoms or something. Then, so previously, previous of the recombination, the proton and the electron exist freely. That means the universe is filled by the charged plasma. So photon cannot go straight because the photon hit to the proton or electron, so it's scattered together. So it's like the situation of if you go to the inside of a cloud, you cannot see the site. But if you go out the cloud, then you can see the very good site. But because the photon cannot scatter anything. So the situation is the same too here. So after the trapping of this proton and electrons, then photon can go straight. And this information around this recombination scale is the temperature is given by, I said the order of the 1 electron volt, but if I said by Kelvin, then it shows we're saying roughly the 3000 Kelvin. This information can measure to the current observation. So as I said, the radiation component expand with the wavelength is also expand by the space expansion. Then the current observation gets just 2.7 kelvins photons. So I explained very quickly about the history of the universe, and in this section I give the basic of the time dependent of the universe given by the Friedmann equation, and so we can get the relationship between the time evolution and what's happened. But I didn't mention about how do we get the relationship between the time and temperature. Actually, this temperature is also very important in the expanding universe, because actually the universe is expanded with the almost homogeneous environment. So almost universe evolved with the locally thermal equilibrium. So we have to give the formulation for the thermodynamics. So we have to explain about this thermodynamic on cosmology, the next section.